Now, in this figure, I'm going to take it in chunks. We're just going to look at the top part first. And we're going to discuss that, we're going to transition kind of into the practical categories of soil water. I add some sciencey terms to it. Okay. So the first one we have is gravitational water, which drains rapidly after rainfall. It contributes very little to plant growth. It just zips right through the soil because of gravity, gravitational water. Capillary water is held in small pores by cohesion forces and represents the main source of plant available water. Hygroscopic water exists as extremely thin films tightly bound to the soil particles, and that water is unavailable to plants. These distinctions set the foundation for understanding moisture constraints. Now, as you're looking at this figure, gravitational water is on the right. So once you reach a certain point, gravity's just pulling the water. You have that happy plant area in the middle, the cohesion water. Okay. Sometimes not all of that's available because even sometimes that cohesion water is still held too tightly. And then on the left-hand side, you have that hygroscopic water, that film that the plants definitely can't access. So let's move to the next part of figure 7.5. So I added a little bit more of the figure. You still have the same top part. And this kind of helps us look a little bit at that moisture continuum. At the top, you see gravitational water that drains freely. And you can see that, the brown represents the soil particles, blue's water. It's full, okay, and water can freely drain through. Then you have this, once you get below field capacity, that's when the soil can't hold any more water and the water excess water drains out. You start to get some air pockets in there. And this is kind of where capillary water occurs, which is held by your cohesion forces and is available to plants. Then you see the hygroscopic water. You might, you get down to oven dry where you dry it in the oven, there's no water at all and you just have pore space. And then you have that kind of in between where there's still water, a water film around especially in the micropores of the soil. And oftentimes that water is not available. Okay. So I like to look at these different levels kind of in reverse of that diagram. I kind of start at the gravitational water side. So you have all the water dumped onto the soil and it's holding all the water it can, and excess water is just flowing through the pores by the force of gravity. Okay, all that water that is just flowing through the system, that's your gravitational water. Now, this kind of in that state, that soil's saturated. Okay, and saturation kind of goes down. That saturation point is just above the point at which the water is all held by soil particles. And there's just a little bit of excess that's kind of trickling through, okay, saturated, right? Then as you begin to remove more water, you don't have gravitational flow anymore. Think of like watering a flower in a pot. You dump water in it. While there's water coming out of the bottom, it's saturated. As it stops dripping out the bottom, Now the soil is holding all the water it can, right? Saturated. As that plant begins to absorb the water and some of it evaporates, you're in this zone of that there's water there that's available for the plant. And that water is mainly being held by cohesive water to water forces, right? It's available. As the water evaporates or the plant uses it, it gets to a point that that plant can't absorb any more water. That's that wilting point. Okay. The permanent wilting point's kind of a border, and oftentimes it's right there where adhesion water is the only thing that's left, maybe some tightly bound cohesive water. And then anything below that, that wilting point, the amount of water below that, or less than that, it's not available for plants. Okay? And that's going to be held primarily by adhesion, very tightly held to the soil particle. And then if you keep drying it, in an oven, say, to where there is no water in the soil at all, that's what we call oven dry. Another way that I kind of envision this is taking a sponge. And this sponge represents our soil. Now you take that sponge and you put it under your sink faucet and you're running water through it, and water makes the whole thing wet and water is draining out of the sponge. That would be saturation. That sponge is saturated and you've got water falling out of the sponge due to gravity. Okay? Now, you let that sponge sit there until no more is dripping out. That sponge is full. If you touch that sponge, some water is going to drip out, but don't touch it. And it's just sitting there and water's not coming out. That's, you're reaching that saturation point. And now water is being held by cohesion. Then, if you would take that almost dripping sponge and squeeze it as hard as you can, you wring out as much water as possible, and then you let it sit there, that sponge is still moist to the touch, but you cannot wring out any more water. So all the available water is now gone. At this point, if there was a plant in our soil, it'd begin to wilt because there is no water available. Now that water that makes that sponge still moist is being held to the particles of the sponge by adhesion. The water is sticking to the sponge. And that is what we call hygroscopic water. Now, if I took that sponge and put it in the oven and dried it until there was no water left, zero water, that's oven dry.